Hello. In this lesson, this last lesson for this week, you're going to be learning or beginning to learn and talk about graphical transformations. We're not going to be doing them all in this lesson. This will be split up. So you're going to be able to translate. We're going to do that. Reflect and vertically stretch functions when given a graph or equation. So we'll look at those transformations with any function today. So let's get started. Rigid transformations, maybe you remember these. Transformations that leave the size and shape of a graph unchanged, right? So a rigid transformation is going to be something like a translation. Let C be a positive real number when the following result in translations of the graph of y equals f of x. So we've got horizontal translation, so let's take a look at this, right? So when you subtract C right here, right, a translation of right by C units, and when you add C, it results in a translation to the left by C units. A vertical translation, so see, I'm impacting y, right? After I take the function and I take the entire function and I add something to it, this is like I'm impacting the input. Right? I'm affecting the x value, that's why it's right and left. This is an impact on, well, I get my outcome of f of x and then I add c to it. So this is affecting y. So when you add c, that's going to move it up. When you subtract c, that's going to move it down. If a graph is translated a units to the right or left and b units up or down in IB world, this is sometimes how you'll see it, right? Sometimes you'll see this notation and that indicates a translation of left or right A, up or down B. So example, f of x equals x squared, right? This might look familiar to you, right? This is going to make that vertex move right C units. The parent function moves to the right C units. This is going to make the parent function move up, right? This would have a vertex of 0, 2. That should be C, sorry. For this notation means that you're going left 4 and down 2. So just knowing what this means, but that means that you're going to move. So what you would end up with, f of x equals, I mean, I guess I could write this as f of x plus 4 minus 2, right? So you'd have f of x equals x plus 4 squared minus 2 would be what this function is. All right, so let's take a look at our first example here. Let v of t equal e to the power of t divided by t. The graph of h of t is this graph is what's given to you. After this translation, we want to write down an equation for h of t. So what exactly does this mean? What does that 2 and that negative 3 indicate to us? This is what I want to know. So this means that we are moving right 2, and this means that we're moving down 3. Right, so how can you indicate that? Well, then h of t is equal to b of t minus 2, that's right 2, down 3. So what am I going to get? Now, e to the power of t minus 2 divided by t minus 2, right? You're affecting all of your t values, minus 3. The parent function is moved right 2 units and down 3 units. And you can see that with a button. You can plug in some points and see. It's not going to be very nice because you're dealing with e, but if you wanted to. Look at a graph. Look at a graph of this and compare these two. How is f of x equals x squared transformed to obtain this? Why might this be a little bit more difficult for me to ask of you? Because we're not looking at it as a composition, right? We're not looking at it in the form that tells us right away. Oh, I want to go back. So, well, maybe we can figure out, put this in vertex form, right? Maybe you're going to do that by completing the square. right? Which we so obviously all know how to do, right? Maybe you're going to figure out what the vertex is, right? So let's do that. Let's do the vertex. Opposite of b over 2a is going to give me the x coordinate of the vertex. So that's going to be 2 over 2, which is 1. And then I'll go ahead and plug that back in to get the y coordinate of my vertex. So that will give me 1 squared minus 2 times 1 plus 7. 1 minus 2 plus 7 is going to be 6. So I'm going to have a vertex at 1, 6. So I could rewrite this as y equals x minus 1 squared plus 6. If you want to multiply that out and check that I did that correctly, go for it. I could also do completing the square. Should I show you that? X squared minus 2x plus 7. I would have to be adding 1 here, so I'm going to have to subtract 1. And then if I factor this, my purpose was to get it as a perfect square. X minus 1 squared plus 6. Whoa, same thing. Right? So my transformation here, right, how is it transformed? It moved right 1 and up 6. Whoa, wrong way. The parent function was moved right 1 and up 6 units. Right, so these are some rigid transformations. A reflection is also a rigid transformation. So if the point xy is reflected over the x-axis, you're going to get this point right here. So if you picture this, and I'll show you guys a graph in a moment, but if I stuck a point right here, and then I reflected it over the x-axis, the x value is not going to change. X stays the same, y will become opposite, right? It's going to be equidistant from the line you're reflecting over. If I were to reflect it over the y-axis, my y value is not going to change. But my x value will become opposite, equidistant from that line of reflection. Right, so remember those rules. Right, so if I have xy and I reflect it over the y-axis, I get negative xy. If I reflect it over the x-axis, I get x negative y. For the function y equals f of x, the following are reflections. If I reflect it across the x-axis, the y value becomes negative, right? The entire function, it's going to go in front of my output. I'm going to negate the entire thing, negative f of x. If I'm reflecting over the y-axis, I'm just going to negate the input. I am negating or doing the opposite of the input, the x value. So find the equation of the reflection of this right here over each axis. So let's start with, why don't we do the x-axis first? So if you reflect it over the x-axis, your y value becomes negative. So that means I'm going to be doing negative y of x. So I'm going to do negative, and this should be a little familiar, right? And what was this true for? Remember we did when you negate something? Kind of when we were talking about odd functions. So remember that this, you're negating it. You're not going to negate the numerator and denominator because that like undoes it, right? That would actually give me the same thing. It's like then I'm multiplying by negative 1 over negative 1, which is just multiplying it by 1. So that's not what we're doing. I'm just going to distribute it to the numerator. So I would say negative 3x plus 2 over 4x cubed minus x squared plus 1. Right? This would be my new function. If you don't believe me, I can show you a graph in a moment. I'm going to write it down, though, so I don't forget what I did. I'm like literally writing on a napkin. We can look at that in a moment. And then if I reflect this over the y-axis, that's not how you spell axis. I'm going to have y of negative x. So my input is going to be negative. So 3 negative x minus 2 divided by 4 times negative x cubed minus negative x squared plus 1. Now let's simplify. Well, in my numerator, I'm going to get negative 3x minus 2. In the denominator, that's going to give me negative 4x cubed, which is going to be minus x squared. Right? Like it's minus, and it's just minus that when you square that, it becomes positive plus 1. Right? I guess I could simplify this if I wanted, right? I could factor a negative out of both. And factor a negative out of the denominator, 4x cubed plus x squared minus 1. And that negative would cancel. Right? That would just give you, that's equivalent to saying 1. I'm going to write that one down as well. Why don't we look at these? Let's look at the graphs. This is going to go away, but that's okay. Let's take a look at Desmos. So what was the first one? Negative 3. Whoa, look, I'm in the screen now. Negative 3x plus 2 divided by 4x to the third minus x squared plus 1. That was the first function that we had. Display mode, projector mode, whatever it's called. And then when we reflected it over the first axis, oh goodness, I got messy in my writing. 3x minus 2 divided by 4x to the third minus x squared plus 1. Ooh. That was a reflection over the x-axis, right? I can see that. That's pretty cool. And then if we go back to that purple one and we reflect it, maybe I should be zooming out a bit. Neat. And then I did the y-axis, right? We made the x negative, and I got 3x plus 2 divided by 4x to the third plus x squared minus 1. I typed that correct? Oh no, this is a minus. I'm all messed up. What was I reflecting over here? Something's not right. And now I don't know what my work was. I can't follow it. Which one did I start with? Was this supposed to be a negative? No. No, guys. Was this negative? Oh no. I don't remember now. Which one were we doing? We were doing reflecting it over. We did 3, and then I did negative x plus 2. Oh, no, that was a minus 2. Oh, do I have the first one set up wrong? This wasn't what I was given. What was I given? Oh, this was the one that I was given. I'm like trying to figure out where I went wrong. I just have the wrong thing clicked. This was the one that we were given, sorry. So if you look at these two, it's a reflection over the y-axis. If you look at these two, it's a reflection over the x-axis. My fault, I was literally clicking the wrong one. Embarrassing. Okay. So there you go. Non-rigid transformations are stretches and shrinks, right? Like dilations. We're gonna focus on vertical for this lesson. So vertical stretches and shrinks. So let C be a positive real number. The following results in vertical stretches and shrinks of f of x. So y equals c times f of x. This is going to be a vertical stretch by a factor of c if c is greater than 1, and it's going to be a shrink if it's less than 1, right? And keep in mind that we started off and we said that c was a positive real number. So this is really saying that it's between 0 and 1. If it's 1, that's not going to change it, right? If you multiply by something by 1, it doesn't change it. So if we have this function right here, f of x, we want to find the equation if it has a vertical stretch by a factor of 3, right? So you're basically going to say 3 times f of x equals 3 times the entire thing. We have not done much with horizontal. That will be in your next lesson. So 3 root x minus 24x to the 5th. I have these graphed on that Desmos. We can go back and look at them in a moment. And then I can do 1/2 f of x equals 1/2 times the square root of x minus 8x to the 5th, which will give you root x over 2 minus 4x to the 5th, or 1/2 root x if you want to express it like that. Right, so this would be a vertical shrink. It's getting, oh, you can't see what I'm doing, versus a stretch. So if we take a look at that Desmos graph again, which I already have, hey, I'm back. This was the original one. This was the stretch by 3. Oh, that's a little not very effective. And then this is the shrink by 1/2. Right, so you can look at them all together and you can see the stretch and shrink. And finally, let's finish up with this example that combines all 3 of these transformations. So you're given this sketch, this graph right here, and this is f of x, and we want to figure out, we want to sketch y such that these 3 things are happening. So let's talk about what's happening. We are going to translate left 2 units. We are going to have a vertical stretch by 2, right? And we are going to translate down 1 unit. So I'm going to take a look at these points, these critical points. So this is -1, 1, 2, 3, -1, -3. That is 0, 2. This is 1, 2, 3, 3, and 4, 2. I need a new color so that I can do this. And I'm going to do these transformations in this order. So the dilation is going to come before I move it down. Okay. Right, order of operations. So there's only one thing happening to x, right? That translate left 2. So this is going to end up at -3. This is going to end up at -2. This is going to end up at 1, and this is going to end up at 2. Right, so then I've translated all of my points. So it's basically like I've taken this and I just moved it to the left. And now I'm going to stretch it by a factor of 2. Well, this would be, is that a negative? Yeah. This is going to be -6. Right, so now I've moved it to the left. Now I'm stretching it out. This is going to be 4. This is going to be 6. And this would be at 4. Okay, I've done this. And now that I've moved it to the left and I've stretched it, I'm going to shift it down 1. So this is going to be -7. This is going to be 2, 3, 5, and then 3. So my points, I'm going to plot the new, so the point -1, -3 after this transformation is going to do this. Right, I'm going to have a new point at -3, -7. This point right here is going to go to 1, 2, 3, -3, -3, oh gosh, 4, 5, 6, 7. Oh, that's very far down there. That's where it is now. Let's see what my graph looks like at the end of this. -2, 3. So 0, 2 is going to end up at -2, 3. Which, oh God. Oh gosh. That's not, I'm like not even far enough over here. It should look parallelish, but that is horrific, my friends. That is terrible. Do better. 1, 5. I'm embarrassed. 1, 2, 3, 4, 5. Should look the same, just like stretched, just like bigger. Oh well, if I had a better graph, this would work nicer. Should I plot the points? No, you guys are like, just stop. I'm gonna stop the video. I could. No, but then I would have to do like the restrictions on it. Okay, it's okay. I'm gonna live with this. I'm embarrassed. I need to get this off of my screen. So we looked at some transformations here, right? We looked at rigid transformations and then one non-rigid to talk about some of these transformations and what they do to the graphs and how you find them. Bye, everyone.